Welcome to the final outcome, where we work with vectors in 2 and 3 dimensions. Vectors are the language of movement and direction, and they're everywhere in physics, engineering, and computer graphics. A vector carries both a size, its magnitude, and a direction, which sets it apart from a scalar that has size alone. Across this outcome, we'll meet position, free, and column vectors, write them using I, j, and k components, and add, subtract, scale, and measure them. Then we'll use the vector equation of a line, classify how lines relate, and use the scalar product to find angles. A quick way to feel the difference: speed is a scalar, but velocity, which is speed in a particular direction, is a vector. Let's meet 3 kinds of vector. A position vector runs from the origin O to a point, so OA gives you the position of the point A. A free vector is defined purely by its size and direction, not pinned to any starting place. And a column or component vector is written out in components such as 3, 4, or equivalently 3i plus 4j. We describe vectors using unit vectors, which point along the axis. In 2 dimensions, we use I along the x-axis and j along the y-axis, and in 3 dimensions, we add k along the z-axis. So 3i plus 4j is exactly the same as the column vector 3, 4, and 2i plus 3j plus 4k is the column vector 2, 3, 4. A unit vector simply has magnitude 1, and I, j, and k are the standard unit vectors along each axis. Adding vectors is wonderfully simple. You just add their components, which geometrically means placing them nose to tail, the triangle law. If A is 4, 1 and B is 1, 3, then a plus B is 4 plus 1, 1 plus 3, which is 5, 4. To subtract, you subtract the components, so a minus b is 4 minus 1, 1 minus 3, giving 3 minus 2, and subtracting b is the same as adding b reversed. The resultant a plus b runs from the start of a right through to the end of b. Let's combine scaling and subtracting in 3 dimensions. Given a equals 2, minus 1, 3, and b equals 1, 0, 4, we want 3a minus 2b. Multiplying every component of a by 3 gives 3a equals 6, minus 3, 9, and doubling b gives 2b equals 2, 0, 8. Subtracting component by component, 3a minus 2b is 6 minus 2, minus 3 minus 0, 9 minus 8, which is 4 minus 3, 1, or in component form 4i minus 3j plus k. The magnitude of a vector is just its length, and Pythagoras gives it to us. For a 2-dimensional vector, a equals 3, 4, the magnitude is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, the square root of 25, a tidy 5. In 3 dimensions, we extend the same idea. For b equals 2, 3, 6, the magnitude is the square root of 4 plus 9 plus 36, the square root of 49, which is 7. Those vertical bars around us simply mean its length. Let's picture a vector living in 3 dimensions, with components along the x, y, and z-axes. The vector A equals 2i plus 3j plus 4k, or in column form 2, 3, 4, has 1 arrow along each axis. Its magnitude is the square root of 4 plus 9 plus 16, which is the square root of 29, about 5.39. Reassuringly, the same rules for addition and magnitude that we used in 2 dimensions carry straight over to 3. A line is completely fixed by 1 point on it and a direction to travel in. We write its vector equation as r equals a plus td, where a is the position vector of a known point, d is the direction, and t is a parameter you can dial up or down. For instance, r equals 1, 2 plus t times 3, 1 passes through the point 1, 2 heading in the direction 3, 1. Each different value of t simply hands you another point along that same line, and it all works identically in 3 dimensions. Let's test whether the point 7, 4 lies on the line r equals 1, 2 plus t times 3, 1. Splitting into components, x is 1 plus 3t and y is 2 plus t. From the x equation, 7 equals 1 plus 3t, so 3t is 6 and t is 2. Now we check the y equation with t equals 2. Y is 2 plus 2, which is 4, and that matches perfectly. So because the same t works for both components, the point does lie on the line. 2 lines in space can relate in 3 ways. They intersect if they meet at a single point, sharing a consistent value of the parameters. They're parallel if their direction vectors are scalar multiples of each other, so they run alongside and never meet. And uniquely in 3 dimensions, they can be skew, meaning they're not parallel yet still never meet, because they sit in different planes. To test for parallel, check if one direction is a multiple of the other. To test for intersecting, solve the components and see if a consistent parameter exists. The scalar product, also called the dot product, multiplies 2 vectors together to give a single number. For A equals a 1, a 2, a 3, and B equals B1, B2, B3, it's a 1B1 plus a 2B2 plus a 3B3. Crucially, it also equals the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between them. Rearranging gives cos theta equals a dot b over the product of the magnitudes, and if the dot product is 0 with neither vector 0, the two are perpendicular. Let's find the angle between A equals 4, 0 and B equals 3, 3. The scalar product is 4 times 3 plus 0 times 3, which is 12. The magnitude of A is 4, and the magnitude of B is the square root of 9 plus 9, the square root of 18, about 4.243. So cos theta is 12 over 4 times 4.243, that's 12 over 16.97, which is 0.7071. And taking the inverse cosine gives theta equals 45 degrees. Now a 3-dimensional example, the angle between A equals 1, 2, 2, and B equals 2, 0, 1, to the nearest degree. The scalar product is 1 times 2 plus 2 times 0 plus 2 times 1, which is 2 plus 0 plus 2, giving 4. The magnitude of A is the square root of 1 plus 4, that's the square root of 9, 3, and the magnitude of B is the square root of 4 plus 0 plus 1, the square root of 5, about 2.236. So cos theta is 4 over 3 times 2.236, which is 0.5963, and theta comes to 53 degrees. The scalar product also gives the quickest test for a right angle. Our A equals 2, minus 1, 4, and B equals 3, 2, minus 1, perpendicular. We compute the dot product, 2 times 3 plus minus 1 times 2 plus 4 times minus 1, which is 6 minus 2 minus 4. That comes to 0. And since the scalar product is 0 and neither vector is the 0 vector, the two are indeed perpendicular, with no need to work out any angles. Let's tie the vector work together. Vectors carry both size and direction, and they behave the same way whether you're in 2 dimensions or 3. You add and subtract them component by component, scale them by multiplying every component, and find their length with Pythagoras. Lines are written as r equals a plus td and classified as intersecting, parallel, or skew, while the scalar product hands you the angle between vectors and instantly tests for perpendicularity, which is why vectors are so central to graphics, engineering, and navigation. To recap, a vector has magnitude and direction, and can be a position, free, or column vector, written with I, J, and K components. You add or subtract them component by component, and scalar multiplication scales every component, while magnitude comes from Pythagoras, the square root of the sum of the squared components. A line is r equals a plus td, and two lines may be intersecting, parallel or skew. And the scalar product, a dot b equals the magnitudes times the cosine of the angle, gives you that angle, with a value of 0 signaling perpendicular vectors. That brings the vector's outcome, and indeed the whole unit, to a close, having covered components, magnitude, lines in space, and the scalar product. For further study, the Further Reading offers core and engineering maths texts, along with the practice and videos on Dr. Frost Maths and Khan Academy. Since vectors underpin computer graphics and physics engines, it's well worth linking these ideas to your programming work. Try a few extra angle and perpendicularity problems by hand to lock the methods in.